Okay, the next reaction we're going to look at is called the Claisen condensation reaction. And let's take a look at the overall reaction before we dive into the mechanism. But with the Claisen condensation, the key feature is you're not using an aldehyde or ketone, but rather you're using an ester. And when you do this reaction, you first treat it with a strong base, something like ethoxide, and then at the end of the reaction, you need to quench with some sort of weak acid. But in the end, what you end up getting out is a product that looks like this. So alpha to the ester, you still have 2 remaining protons. And then beta, you've got a ketone. So what this was referred to as is a beta keto ester. And it's the result of a nucleophilic addition of an enolate to a second equivalent of the starting material, kind of similar to what we saw in the aldol reaction. I did want to make an important note though, and this note has to do with the base selection. So up here I said that I wanted to use sodium ethoxide, and that was on purpose. I want to be sure to match my base with the alkoxy group on my ester. That way I can avoid any unwanted transesterification. So let's make a note that the alkoxide base should match your ester. And like I said, this avoids transesterification, meaning we're not going to accidentally create a new type of ester. So for example, if we had a methoxy group rather than an ethoxy group, then we would want to use sodium methoxide here. We just want to make sure that we've got things matched. All right, so let's take a look at the mechanism for this. It's fairly intuitive, especially if you understood the aldol condensation mechanism, but let's go through it piece by piece. So first we have this ester, and it has alpha protons coming off of this position. So we've got 3 alpha protons, and we've got sodium ethoxide. In this case, it's going to grab one of these alpha protons, and under equilibrium, we'll create a portion of our enolate. And like I said before, you can show either resonance structure, doesn't matter to me, and you can assume that there's going to be some unreacted starting material. So this, I'm just going to make a note, is unreacted starting material. So not all of it forms our enolate, only a portion of it does, but the portion that forms the enolate can attack in and kick electrons up to that oxygen. All right, so now we're getting somewhere. We are going to form a new carbon bond. I'll show that in orange. We've got an oxygen with a negative charge. We still have our ethoxy group, and then we have our methyl group. All right, as you can imagine next, we've got this leaving group right here that we can essentially kick off. So in the next step, this negative charge is going to clamp down and kick off ethoxide as our leaving group. Essentially at this point, the reaction is no longer reversible anymore. So we will end up forming our final product where we have a new covalent bond. We reform a ketone, and then we kicked off ethoxide as our leaving group. So just like I said before, this is going to be catalytic, meaning your leaving group can act as an additional source of base and keep this reaction going in the future. So it's a pretty useful tool for making new carbon-carbon bonds. All right, so you can see in this example, just like with the aldol example, both of our reagents were the same, meaning we were reacting an enolate with some portion of our unreacted starting material. We can actually do this in a similar manner with two different starting materials. And that's called a crossed Claisen reaction. And let's take a look at how that works. So one way you can do this is pretty straightforward, where one of your starting materials is an ester. But if you notice, this ester has no alpha protons. So I'm just going to make a note, ester without alpha protons. Meaning there is an alpha position here and here, but neither of those positions have protons off of them, so there's no way we can do any sort of enolate chemistry with it. Okay, and then the second thing we need is some other ester or ketone that can do our nucleophilic addition. So in this case, we need some sort of enolizable starting material. So I'm going to make a note here. This could be anything with alpha protons, which means it can form an enolate. Okay, and as you can imagine, if we go ahead and treat this with a base, we would want to make sure that the base matches the leaving group on our ester. So it'd make more sense to use something like sodium ethoxide to ensure that nothing unique happens there. And then in step 2, we're just going to treat this with our acid. All right, so now the question is, well, what product would we get out? So I'll make this worth 4 points. And like I said, there's no shame in drawing out the full mechanism for this. So let's practice. And in this case, I always like starting with the thing that we know will form our enolate. So in this case, the only thing that can form our enolate is acetone, because it's our only starting material that has protons coming off of an alpha position. So we've got ethoxide floating around. This ethoxide can grab this proton and clamp down. So let's go ahead and show this enolate. I'm not going to bother with equilibrium arrows here because we know the net reaction isn't reversible. And we've got our enolate. All right, now we'll throw in our second ester. So our other reagent we said can't form an enolate, but it can act as an electrophile, right? So in this next step, I'm going to go ahead and kick up electrons to that oxygen. All right. And when I do this, I'm going to make a new carbon-carbon bond. I'm going to show that in orange here. And then over on this side, I'm going to have my oxygen with a negative charge. I'm going to have my ethoxy group. And then I'm going to have my phenyl group. So that bond in orange is new. And then in our last step, we can clamp down and kick off our leaving group. And we can end up with our new product. I'll keep this new bond in orange, where we have a new ketone. So as you can see, this even works if you're working with something like a ketone that can form an enolate. The key feature is you're reacting it with an ester as an electrophile, because if you have an ester with an electrophile, you can kick off this leaving group and get some sort of carbonyl formed, which is kind of unique. All right, so let's try a challenging one. This one's going to be tricky. All right, so this one is kind of unique. What we're going to do is have one starting material. So let's see. We've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There we go. I want to make sure I had the right number of carbons. And so we've got this diester here. And what we're going to do is we're going to treat this with sodium ethoxide. Again, we want to make sure that this alkoxy base matches our alkoxide group on our ester. That will be step 1. And then step 2 will quench with weak acid, and we want to figure out what in the heck is made when we do this reaction. Well, let's try it. So in our first step, I'm going to have ethoxide as my base. And if we think about where the alpha positions are that have protons, we actually have 2 alpha positions right here and right here. Both of those have protons. Does it matter which one we go after? Not really, because it's a symmetric molecule. Regardless of which side you go after, you're going to get the exact same product. So I'm just going to go ahead and focus on these alpha protons over here, and we're just going to pluck off one of them with my base. And by doing that, we're going to make a portion of our enolate. And we'll get a negative charge there. All right, so now the question is, well, what happens? Well, there is a probability that this intermediate that we've formed reacts with some of our unenolized starting material, but there's actually something better that can happen. Anytime you can form a ring rather than reacting with another equivalent of reagent, that's typically favored because you're not increasing order, right? Going from, let's say 2 moles to 1 mole is entropically disfavorable when forming a ring is just 1 mole to 1 mole. So what happens is this negative charge will actually attack the other side, which makes sense because this would be carbon 1, 2, 3, 4, and 5. We would end up forming a 5-membered ring. 5-membered rings aren't as good as 6-membered rings, but they definitely do occur. Okay, so let's go ahead and draw this. And when I draw that, I know I'm forming a 5-membered ring of all carbons. So I'll go ahead and I'll draw that out. And I'll just arbitrarily number this. Got my 5-membered ring. And off of carbon 1, I know I have this entire group here. So I'm going to go ahead and draw my ester coming off of carbon 1. Carbon 2, there's just 2 hydrogens, same with carbon 3 and 4. And then if I go over to carbon 5, I should have an oxygen with a negative charge. That's where I kicked electrons up to. And I should have my ethoxy group. All right, so we're not quite done yet. In the next step, what occurs is we clamp down and we kick off ethoxide as a leaving group. And by doing that, we reform a CO double bond, and we've got ethoxide. So we've already been able to kind of problem solve our way to this, and we know that this is going to be our final product. So if we wanted to, we could even plug it into this box and get to our final answer. These do take a little bit of patience as you work through them, but the more you practice the mechanism, the less overwhelming it is to work on these problems. This reaction is kind of unique. This is called an intramolecular reaction because it's reacting with itself. Specifically, it's an intramolecular Claisen, which also has a special name. This is called the Diekman Cyclization. So it's kind of a special reaction where you can form rings. All right, you can also do intermolecular aldol reactions as well using similar chemistry, but typically you end up with an alpha-beta unsaturated ketone or aldehyde, or you end up with a beta hydroxy group. In this case, we're ending up with this unique product. All right, I know it can feel kind of overwhelming, so I did want to show you a couple of brief hints / trends to look for. All right, so let's say in a molecule you have 2 carbonyl groups that are arranged like this. We're just going to imagine that this is in the middle of some molecule. And they're essentially on not adjacent carbons, but one further away. So they're 1,3 substituted. If we ask ourselves, well, how can we make this? This can be made via the Claisen reaction. So Claisen reaction with esters is good for 1,3 dicarbonyls. Let me zoom out a little bit. So really, this is the same chemistry we've seen above, right? If we look at all of these, for example, 1, 2, 3, we've got carbonyls in that same orientation. If we go up and we look at the one above this, we've got 1, 2, 3. This was also a Claisen reaction. So it's a really good way of getting 2 carbonyls situated like that. All right, let's take a look at the next one. In this one, again, you could say that this is the alpha position and this is beta. So really we've got a beta hydroxy group. So this is good when doing aldol chemistry. So aldol reactions are good for making beta hydroxy aldehydes or ketones. And I know every year I see a student that says, well, can't we just go from this to this by using PCC? Well, I suppose so, but that uses chromium-6 and it's pretty nasty stuff. I would prefer to avoid using any chromium-based reagents if possible, so the Claisen reaction would be a much better solution for that. All right, last but not least, what if we have something that looks like this? Again, this is the alpha position and beta position, and we've got a double bond there. You can make these with aldol reactions as well. So this is aldol reactions with heat are good for making these. Alpha, beta, unsaturated ketones or aldehydes. So I know it is overwhelming when you're looking at some of these synthesis problems, but like I said, if you ever get stuck, trust your gut, do the mechanism, double check your work. You can always email me too if you need me to check anything, and I'd be happy to help you out. All right, good luck studying.